Thank you, Professor Perkins, for the very kind introduction, and thank you all members of the NCIT Transportation Center for the kind invitation. It's really an honor to present, given the fact of who previously presented in this series, and of course the membership of this UTC. So thank you very much. Yes, indeed. I just came back from 150 miles coming from Duluth to Minneapolis. But it was very meditative and helped me change and redesign the presentation that I hoped you guys enjoy and get something out of it. I'll try to be as succinct as possible. I promise not to show you too many equations, maybe just one equation. And so I also want to emphasize that I'm going to provide some examples, some projects about geotechnical research with the goal of trying to emphasize the importance of geotech research for supporting strategic goals of an agency. In this case, Minnesota Department of Transportation. I'm currently employed at MnDOT, have been working here for about 6 years. And I want to emphasize this is what the projects that I selected and what I want to explain is about supporting strategic goals, so long-term goals. As part of geotechnical research, we also provide support for immediate needs, project delivery needs. So that part I'm not going to cover in. I'm going to cover in strategic goals and how we can support that effort. So before I start showing examples of the projects that we have completed and are currently in progress to support strategic goals, we have to first review what the strategic plan from MnDOT. So let's go. So this is all information I'm going to present. The next few slides are coming from the strategic plan published by MnDOT. You can access it on that website showing in the corner. So what is the vision for the strategic plan? The vision is Minnesota's multimodal transportation system maximizes the health of the people, the environment, and our economy. What is the mission that we have is connect and serve all the people through a safe, equitable, and sustainable transportation system. And what are the values? Our values guide how all MnDOT employees show up each day on behalf of the Minnesotans. So what are the values that we have here? We have safety, service, equity, sustainability, innovation, and collaboration. And I want to highlight what values overlap with the work that we do as geotech researchers. And those values are highlighted in the slide. Our values corresponding to sustainability, innovation, and collaboration. I really like to share some of this information in general about MnDOT for whoever people that are not familiar with the Minnesota Department of Transportation, and this information is included also in the published strategic plan. Interesting to know that Minnesota is the fourth largest public road, manages the fourth largest public road system in the nation, about 12,000 center line miles of interstate highways. We complete about approximately 200 projects, construction projects every season. And we do have about 5,000 employees, so it's a pretty large enterprise. So you can start seeing some of the issues that we can have potentially with implementation and of research, of geotechnical research, due to the large size of this enterprise. And we manage about 4,600 bridges. So in terms of support, geotechnical support, we kind of work in pretty much these three areas. Of course, helping support managing the interstate highway system. We provide support during construction when issues come up. And of course, foundations related to bridges and other structures. So those are kind of the three areas where we provide geotechnical research, provide support to MnDOT. So what are the strategic goals? We have 5 strategic goals at MnDOT from the plan. We have promote a safety culture, advance transportation equity, be a champion of sustainability actions, maximize the stewardship of resources, and foster a thriving workforce. And out of these 5 values, these 2 are the ones that mostly geotechnical research supports in terms of uh, implementation of those goals. So what are the implementation principles that we have at MINDAT? Are the following ones. Making progress on the strategic goals will require a collaborative and flexible approach, and I would like to highlight that the flexible approach and the collaboration, that's key and fundamental. We will also leverage existing plans, committees, measures, and proven strategies whenever it's possible to expand our capacity and increase our impact. So that means we learn from our past, or learn from experiences. We're trying to take what we did before to move forward. Where MINDAT has an established and long-standing track record, we'd like to rethink our approach and trying to innovate. So we don't want to be stagnant. And that's why research is so important for MINDAT, is because we want to keep improving. We want to be more efficient. We want to rethink the ways we do business and deliver our products. And where objectives and strategies are emerging and less defined, we will explore research and collaboration with our partners, such as universities, such as contractors, or other entities that are part of the industry. So I want to just emphasize those two goals. And moving forward, when I start showing the examples of the projects, I'm going to have these pictographs right next to the title, just to show each project what kind of goal or strategic goal that project supports. So for the goal of be a champion of sustainable actions, what are the strategies? The strategies include preparing MINDAT for extreme weather that is already impacting our infrastructure, and we'll show you some examples. And to work with materials and processes that reduces emissions. To maximize the stewardship of resources, what are the strategies that we have? We want to use best practices, and this is very important, data-informed approaches to ensure that construction, technology, and other agency projects are on time and on budget. We want to also, part of the strategy for this goal, for the maximizing stewardship of resources, we want to implement our asset management plan to maximize the useful life of our pavements, bridges, and other critical assets. What is very important when we're trying to implement and to meet the strategic goal of maximize the stewardship of our resources, we need to prepare for emerging technologies with national research partnerships. So, for example, this center is extremely critical to accomplish that goal. Training and scalable pilot demonstrations. That's super important for us. Accelerate pilot and scale innovations, scaling up technologies that are very well mature in the lab is also critical for us to improve our efficiency and to provide effective services to our customers, which is the public. What is also very important, I really like, something I really like about my job is that MINDAT really appreciates innovation and encourages their own staff to innovate, even if there are small tasks. So MINDAT values employee-driven innovation, and that's why I highlighted here in this slide. And the continuous improvement through communities of practices like TRB, like a Center for Transportation, like other collaborations, and through leadership support. So now that we have clear with a big picture, what is the strategic plan for MINDAT, now we're gonna go through the projects that I have examples and to just highlight and to show why geotech research is extremely important to support that strategic plan for a large agency like MINDAT. So here in this slide, I have the projects I'm going to be covering today. In green color is the ones that are completed, and the orangey, yellow, I'm kind of colorblind, are the ones that are in progress. Okay. I like to present, usually when I present research products to the public or to internally, I usually like to present those in the context of a life cycle of the asset to keep me in line and to keep me with a big picture of the life cycle of that specific asset. So I just put each project right next to where approximately in the asset life cycle stages that project has an impact on. So for example, during the planning and design process of a highway, these projects, the vulnerability of slopes play a fundamental role in supporting those activities. The development and implementation of the use of the lightweight deflectometer for quality assurance of pavement foundations, super important during construction, of course, of pavements. So that's how I lay out this framework. So I'm going to keep coming back to this asset life cycle as we move along these projects, these example projects. So let's start with a simple one. Simple, yet it took a long time, many years for be fully implemented. And to my professional opinion is right now a success, which is the implementation and the use of lightweight LWD for quality assurance of pavement foundations. So you can see moving forward for each product, for each research project, I'm going to have next to the icon, the picture graph that describes this which strategic goal this project is supporting. Okay. So as we all know, density does not determine stiffness or strength of your material. Kind of a photo, a picture is worth 1,000 words. You can see here a pavement foundation where it passed density, but obviously didn't pass strength, stiffness. It failed during proof rolling. And I like to usually explain this in simple terms using these synthetic soil structures. So why it's important to move away from density-based quality assurance for pavement foundations to more performance-based using some fundamental measurements like stiffness. It kind of describes, it's nicely summarized in this schematic. So we have here soil 1, soil 2, we have the same densities. So row 1 and row 2 are the same densities. However, because of the fabric and the internal structure of these two soils, the modulus, the stiffness, the slope of the stress strain curve of these two soils are significantly different. And the same with the strength. So same density doesn't necessarily mean the same stiffness and strength. And therefore, well, we want to move away from using density alone for quality assurance and more a performance-based stiffness measurement. Also, we want to do that because we want to be better at the workflow of connecting those stages of the life cycle of the asset. So if I go back, there is usually a disconnect between the design and the construction. Usually during the design stage, for example, for Minnesota case, we use a mechanistic empirical pavement design. So we need to input during the design stage stiffness to compute stresses and strains. So if we measure density, we cannot do anything with that. So these two will be disconnected in the workflow of the life cycle of this asset. So although it's not perfect, LWD starts giving you an idea of what really that measurement for the side input is all about. So you're starting to connect these two stages of your life cycle. So that's why another reason why we wanted to implement LWD. Keep in mind that the work done for implementation of LWD was done by many other people before me. Some of them already retired. So I'm just here presenting the results on their behalf, all the amazing work done by my coworkers and previous staff from Mindad. So for compaction compliance, after we did all this extensive research, we modify specifications for quality assurance of your pavement foundation. Pavement foundation includes your base, your sub-base, and subgrade. So what do we have for compaction compliance in Mindad? We have something what we call specified density, which are Proctor tests, moisture, sand cone, and nuclear density. So the classical old school tests that you do to check your material. We have also something called quality compaction, which is related to engineer judgment and experience. So it's visual inspection of your foundation as they build. Then we have DCP, penetration index testing, highlighting the LWD and test rolling. Okay, so for the LWD, during the process of research development, there were two methods to assess the performance. One was the deflection base and the modulus base. We developed charts, we developed parameters that according to your gradation and your moisture content, you have a limit for the specific situations, specific materials. So for deflection base, we listed limits for how much deflection we allow. However, we noticed it as we were trying to implement this research that was a little bit tricky. Engineers and technicians are used to more rounded numbers. So 0.34, 0.71, 0.56 is kind of hard to absorb and to comprehend. So it was easier to move into modulus base. We have a better grasp of the numbers related to stiffness. And thus, we encourage our materials and soil engineers across Minnesota to use modulus base. We still have the option of using deflection base, but we mostly use modulus base. And pretty much after many years of testing and experience, we came out with these minimum values for elastic modulus based on the LWD. If you have a granular material, if you have a clay or clay loam soil, or your base or reclaimed material, these are the stiffnesses that we target in megapascals. It's pretty straightforward. So far, we have been pretty successful. These numbers match pretty well the performance. We haven't seen any major failures with respect to this simple, very simple specification for quality assurance. So early on during the implementation of this technology, we'd have very few districts using this technology. Just to go back a little bit and provide you some background, we have 8 districts across Minnesota, in MINDAT, and then we, with the Office of Materials and Rural Research, we are part of central office in Metro, and we provide technical support to all districts. So through all this implementation process, we also got lucky. We also got lucky because manufacturers start miniaturizing the LWD. One of the main issues that we have for implementation was super heavy device. Some of you probably have experience with it. Carrying that, so we used to have 2 people carrying this big device to go and test it out in the field. So the miniaturization of this device is making things much, much better. And now we have kind of an exponential use. So this chart shows about 22 LWDs all across Minnesota. And I think that number is pretty old. I believe we have way more LWDs now being used. Some of the results coming out of the research that we completed are the testing constraints. So LWD cannot be used when the embankment thickness are less than 1 foot, when your base or reclamation thickness is less than 4 inches, when you are testing between 3 feet of water table. That's very important to know as a restriction. You need to perform right after compaction. As it's obvious, you don't want to wait until it rains or it gets too dry. You want to get it right after the compaction, so your environmental conditions doesn't change much. And test when the air temperature is between 36 and 120 degrees. And another one, super important, it's kind of obvious, is make sure that you don't test when soil is frozen. So one of the objectives of doing this LWD research and what we wanted to move away from densities, we wanted to avoid the disconnect between the design specification and the construction quality assurance. We wanted to highlight the importance of fundamental engineering properties such as stiffness and strength, and we wanted to use that so we can connect with our ME-based design. We wanted to also be able to better quantify alternative materials. Using just density and all these classical tools were not good enough to really check the performance of innovative materials. And we also wanted to be better at rewarding good construction. And this tool that's much better job for us than the previous standard technology. So that's it with respect to the simple LWD technology. Now I'm going to move into a little bit more complicated topic, which is assessing stability of slopes across our interstate highway system. So first, I'm going to go through a tool that we developed for assessing the vulnerability of slopes based on geomorphology. And what I mean by based on geomorphology is based on the assessing the shape of the land. Okay, so just give you some context and some examples of why extreme events are becoming more important for us, and why these research projects are super important for MINDAT. Is an example of what happened in 2012. We have an extreme rain event season in June 2012 that caused major salt failures across Minnesota. It cost about $50 million in damage to repair. You could see even from satellite the damage that occurred. So during the rain and flooding, the southwest corner of Lake Superior, you can see here, became muddy and brown. So you can see how massive the event was. You can see June 19 and 20, we have intensity rains of between 7 to 8 inches where we have all these major failures. So that just give you some context of how important this is for us, Minnesota. This is a photo, an example of one of those failures. Jay Cook Park, super popular place to go hiking and go vacation with family. Major failure. So we have had about 26 road closures on our Trunk Highway system after this event. It was a major team effort. We have many agencies working together, MINDAT, DNR, DPS, local law enforcement, federal highway consultant contractor, working as a team trying to solve and fix this as quick as possible to have the system back online. MINDAT main damage areas, we have Trunk Highway 210, in Jay Cook, in Thompson, Trunk Highway 23 in Fond du Lac, and Trunk Highway 2 from Proctor to I-35. So those are the major failures that occur. So that's why it's super important to have a tool that can help us assess the potential problems that we have, be proactive about it. So that's why we have we completed this project. We hired WSB as a contractor to help us with this project. So the idea behind this geomorphology-based tool for assessing slope stability is to assist engineers to proactively identify and mitigate slope risk along the interstate highways and help during the project scoping. So during that planning stage that I showed you early on in that cycle, and long range planning. So how much leadership and planners have to put money in 20, 30 years from now that they can proactively start mitigating some of these risky zones. So that's part of their long range planning. They actually have used this information to inform themselves to be better about estimating the amount of budget allocation in the for the future. We also use this project to enhance our risk-based assessment of our assets. So in summary, kind of what this tool is all about is using a geographic information system, a GIS model, uses the geomorphology, very much the shape of the land, and also other key geological and geotechnical parameters to provide a vulnerability rating or a probability of failure. This model uses the geographic weight regression, or GWR, to account for that local variation on key parameters and minimize the bias and uncertainty on the assessment of this probability of failure. So again, we wanted to have this tool that can help us predict or be proactive about identification of potential failure. So this is one example of a deep-seated failure along Trunk Highway 67 in Minnesota. So what was the process of developing this model? We have these 5 stages. First, we selected some primarily input parameters, or what we call vulnerability factors. I will list them in the next slide, and potential interaction terms. And all of them are based on geomorphology and geology of the region. Then we check the vulnerability rating using these preliminary inputs and with historical slope failures. So we check with past failures history to see if these parameters were predicting good enough. After checking that, we revise those final input parameters, check which ones were the most statistically significant to minimize the complexity of the model. We went back again in the field, verified the model, and we did further adjustments. I promised you I was going to show you just one equation. This is the equation. This is how we compute probability of failure based on this exponential function, and this C is basically a linear regression function. And these are the parameters that I'm going to list next, which are pretty much related to the shape of your land, where the water table is, and other geological factors I'm going to list next. So because Minnesota has a very complex geology, we decided to split the project in phases. So we have the project started in 2017 and culminated in 2020. So using colors, which phases, and for each phase was clumped according to similar geology. So here we listed the kind of parameters that were important for each phase and for each region of Minnesota. That was the initial geology, and the final parameters are listed here on the right. So for example, for phase 1, which included like mostly metro area, the most important parameters for this geomorphology-based model were slope angle, terrain curvature. So if the curvature was concave or convex, how closer was to rivers, distance to stream, the slope, and how close was to a bedrock outcrop. So this is just an example. And depending upon where in Minnesota you were located, the parameters were slightly different. So the team went and verified. They did some preliminary runs. Then they went back, looked for history. They went in the field and adjusted those parameters to get a better match with reality. So this is I'm going to show you an example here on the right. You have here some trunk highway. So we're going to go from satellite photo to elevation. So, and then from elevation, they do the analysis, the regression analysis, and get the red, bad part, bad, highly susceptible, yellow, not as bad, and green, good. So that's an example of a calculation. Now, after that, we came out with a preliminary risk matrix. Just to remind everybody, risk is the computation of is a product of how likely is your slope or your asset to fail or to meet a requirement. So in this case, slope is what is the likelihood of failure. That's coming from your model output. From this case, this regression, this geomorphology-based regression model, and then multiply by the consequences. That's the part that is super tricky, and we still need to work more on this part. For this project, this was very preliminary. So this part, the consequences part of the matrix, was very high level. So of course, if you have a major highway that carries a lot of traffic, that is the only one that communicates to town, that has a high consequence of failure. So that's a critical segment, and therefore you'll be ranked as critical. Okay. So then you multiply what likelihood of failure times the criticality, and then you got those three colors. And then from there, we kind of from this risk matrix, we created what we call the preliminary management areas. And these management areas pretty much delineate areas in your GIS map with similar risk ranking. So then we can easily manage the risk for failure. Interesting enough, materials engineers across the state started using it, especially for regions where we have more susceptibility for failure. So in this case, in Trunk Highway 22, we have a couple of slides happening in July 2020. And the materials engineer used this map to detect where the failure was occurring and potential future failure. So it was pretty nice. The model was able to capture that. So in summary, we were very happy with this tool. This GIS model helped us identify and map and categorize slopes that are vulnerable to failure that can potentially affect that highway system. It helped us in assess the risk during project development. It's kind of a time efficient. It's pretty fast. Geotechnical approach we're going to talk about later can be time consuming. It can be very complicated. So this is very good. This was a very good tool to do first at network level, a high level analysis. Then we can just zoom in and narrow down and focus on specific critical areas, the red ones. So that, in that sense, was pretty efficient. It was model was based on that, is data driven, so minimizes the bias of the engineer judgment. So that's pretty good too. Time efficient approach that can cover large geographic areas. That was also very powerful. That covered the whole state. And it's been used to, this tool is being used for geotechnical asset management. So it was very good. The geomorphology-based model we've been successfully used. Now there were some remaining tasks to be completed, and that's how the next project, which is geotech-based, came to life. What is the motivation for this new project? Are listed here. The six objectives. And what I like about this project is we managed to, because we have a very flexible partner, in this case, Michigan State Dr. Congress, managed to help us modify the objectives so we can accomplish several goals. In addition to be strategic with the big plan, big picture from MINDAT leadership, we also want to develop internal capacity. We want to get up to speed with new available tools that we have available in the market as geotechnical engineers in our sections. So we kind of adjusted the work plan and get excited about this project because we're able to accomplish several other objectives with this. So motivations for doing this project. First, we address recommendations and gaps from the previous studies that I just showed you. And mainly the main concern that we have from the previous project was that we have a lot of red zones. It was pretty unrealistic. It was about 2% of the area of across the interstate highway right-of-way areas. So about 2% of the whole state was showing red. So we thought that was pretty large, that number. So we wanted to move away from geomorphology based to more geotechnical based to see if that still holds true. Second, help implement advanced geotech tools such as 2D and 3D modeling software tools that we have currently available, like Plaxis and other Bentley suites that we part of the Bentley suite. Number three, assess the value of the advanced remote sensing, such as drones, for geotechnical applications such as assessing slope stability. Number four, improve the quantification of risk. So getting a little bit better at computing the probability that I just showed you before, using numerical methods that are commonly available. So let me give you a quick example for that. So we understand that nature is variable. One of the things that I love about geotechnical engineer is there is a lot of art on it. There's a lot of guessing because it's the material that we deal with is made by nature. It's not man-made. So we have a lot of variation. So let's say this distribution corresponds to your strength of your material that you have in your slope. So because you have this information, and we have tons of that information from lab, from field testing, such as CPT, SPT, and others, we can come up with this distribution. And because now we have such powerful computation tools available, we can compute many thousands of runs of simulations of that specific slope, and they get a very good idea of really my probability of failure. Really get it, nail it down to be more accurate. So if I really want to know, I have two mitigation techniques, or if I don't have any mitigation, what is my probability of failure? What is the probability of, in this situation, I have factor of safety being less than 1. For this scenario, 20%. If I modify a little bit my slope, I run out again thousand simulations with some distribution of parameters. I go back and say, oh, I improved it by 40%. So really, I'm nailing down my estimation of vulnerability and probability of failure. That part is also very exciting, something that we're doing with Surya and his team. Number 5, help with geotechnical asset management. So part of this project, we are trying to develop some forms that people in the field can go and assess how risky is that slope. And that's part of the geotechnical asset management program. And last but not the least, as I mentioned, we really want to develop internal stuff and make them feel comfortable using these technologies. And these I want to call it quote unquote advanced because now they're becoming very user friendly. So examples. For this project, this is ongoing. So I'm just going to briefly show you some preliminary results that are shared by Surya and his team. We have a complicated site up in North Minnesota in Climax. We have two failures that are occurring. One near a bridge. We have a bridge here. And then here we have another slope failure occurring, what we call it the north side. We have several instrumentations installed, a lot of geotechnical exploration. What I want to highlight here is that one of the objectives that Surya is helping us with is improving this workflow and trying to implement these advanced technologies. One of the big barriers is we get a lot of information coming from this, not just from the sensors, but from remote sensing and from capturing the digital terrain, the 3D surface of these sites using drones. So here an example, we have about 155 million points. Processing that information in that laptop could be time consuming. You need a supercomputer to really process that. So we want to implement it. We want to make sure that we can use that. So he's helping us out how to downsize it to a model that is accurate enough to provide us enough information to do our geotechnical analysis. So here an example of that failure. It captured the volume, the approximate volume of influence, counter plots of the risky zones. The other thing that is super nice about this project, we have a bridge. We also have railway here. So we have to interact with another agency. There is another asset that is at risk. So this 3D model is helping us out explain the failure, because the failure has been puzzling some of our engineers in the bridge office and geotechnical office, because it's a very weird. This bridge here is moving in a very strange way, and we want to know if this failure here is interacting with the one at the north. So these tools allow us to get better insights. So some examples of Surya's computational stability allows you to compute volume, how much volume if we decided to do some sort of reinforcement, we can really nail down computation of quantities. We can go back between 2D and 3D to validate our simulations. People feel more comfortable, some geotechs feel more comfortable living in the 2D space, so we can go back and forth between the 3D model and 2D model with this project. So that's it. This is progress. Hopefully, in the next few months, we'll have more updates. So stay tuned about this specific slope stability project with Michigan. All right, now we're gonna go back to payments. I'm gonna switch back to payments. And I'm going to talk a little bit about payment foundation uniformity, also known as intelligent compaction. Our previous speaker talked a little bit about it. I think he's a champion, the professor from Portugal on IC. So I don't want to explain much about what really the technology is all about. I'm just going to show you some results on how we're trying to and helping the community with implementation of using IC in payment foundations. So in order to do that, we are lucky. We are, I would say that we're blessed to have a facility, one kind of facility in the world, test payment facility, Minroad. Many of you are familiar with it. Many of you have visited. Many of you have sweat and have tears working there. I see some list people here in the webinar. So built in the 90s, many sensors installed, many experiments. I think it's probably the only one called region facility in the world. I will say you can test your products to the limit, because this facility experiences all kind of extreme weather. You have the cold winter of Minnesota, then you have the hot summer, then you have this shallow groundwater table, you have these ponds that push water into your cross sections. So really is to put your technology to the test. We have great staff helping us there with managing the instrumentation, doing the stress survey, managing the facility. Furthermore, we have one lane which is subjected to real traffic. This is Interstate 94 going west. So Minneapolis is right here, St. Cloud is right here. And then we have a closed loop where we have controlled traffic. So pretty powerful facility that we can use to work with our research. Just an example, we have about, since the construction of this facility, about more than 15,000 sensors installed. And we have about 1 billion total values of temperature measurements. And I wanted to list this because I'm going to show you the last project I'm going to show you is related to temperature. So I just want you to just give the context of this big data that we have available for researchers, and it's public. Everybody can access this information. So we use this, just show you an example of the kind of data we have at MinDat. Very meticulous. We strive to be rigorous about calibration functions for the sensors that we apply, really understanding how the sensors work. So in this case, I'm showing an example of moisture content, variation with seasons, and how it relates to environmental impact, environmental stressors like precipitation here in blue, and how that moisture relates to really construction conditions. So here I lay out boundaries of what we measure during construction, and how that, in this case, sensors installing the foundation, how deviate from the ideal conditions during construction. So very detailed information that we have available to track performance of our assets. Just to give you a context of what Minrod does for researchers and the quality of data. So payment foundation uniformity, Minda has been a champion for IC technology probably since the 80s. Now we are focusing on trying to see connect the dots. And what I mean, we tend to do research, we do the test. In this case, we do the mapping. We see some preliminary trends and then move away. But now we want to go back and look at the performance and trying to connect what happened at the top layers when we do intelligent compaction in your foundation, and how important foundation uniformity is for performance by looking at uniformity using IC with performance. So that's the idea behind this. So this experiment was done by Ingios, by David White in 2017 at the low volume road. So we have sections 185, 186, 188, 189. 185 and 186 are founded in clay subgrade, and 188 and 189 in sand subgrade. However, what I'm presenting here, transverse cracking tend to be mostly driven by asphalt, by the top layer. And in this case, these four sections have the same PG grade binder on top, the same mix design. So really, there was no difference in the AC. So in theory, it should have been performing the same in terms of transverse cracking. However, section 189 show more transverse cracking in 2019. Here I'm showing you the mapping. So you have cell 185 here and 186. So about from here to there is 186, 185. Keep in mind, coefficient of variation on average for those two cells was 29%, coefficient of variation for your stiffness after the mapping. And then I want to show you now, I need to clear up first now, erasing. And now you have sections 188 and 189. So 189 is approximately from here to there, and 188 is this here. On average, we have a 34% coefficient of variation for both, so significantly more than 185, 186. But you can see from the color contours here that variation in 189 is significantly higher, indicating that pavement foundation uniformity has an implication in your distress at the top, and therefore super important. That was 2019. Now we have a good collaboration with Michigan State. We have some interns sponsored by NSF. Came and did work with us, Dr. Fayyaz Sadiq. Now we did more analysis, same data that was collected in 2017. Now we see performance in 2024, and then we start seeing visual cracks coming up, very large cracks that really match where we have large differential in contrast, where we have high non-uniform conditions, where we have high contrast or stiffness, when we have high variation. Although they have very similar cross sections, these two cells, the ones that are not performing well are the ones that have non-uniform conditions. So very important. And our experiment that showcased the same situations where we have high contrast in your stiffness from mapping is showing where it's exactly matching where the crack is starting to visually be starting to show. So now we're curious. We want to keep looking at these cells and keep analyzing if wherever we have those stress change. I'm sorry, those contrast in stiffness are where our distresses are coming up. So that's in terms of uniformity. And the last project I want to present is on something that I'm very excited recently. We're working together here with some other members of our research section. Is on using pavement temperature as a surrogate of pavement performance. So as a pavement engineers, we tend to focus on, we have three mechanisms that affect our pavement system, right? We have stress strain, so it's a question of equilibrium. Then you have your heat transfer problem when temperature changes. And then you have your flow, moisture flow, water flow. So we tend to solve these three mechanisms independently, although they are coupled and they influence each other. We tend to indirectly account for that by when we compute our stiffnesses for our steel or from top material to account for the effect of temperature, of course. So if it's softer, my asphalt will be less stiff, and so forth. Then we include we include indirectly the effect of moisture and so forth. But we don't tend to look at everything more holistically. So here, the idea behind this is through understanding that all of those three systems or three mechanisms are interconnected. So if you have a crack in your road, that's going to facilitate the seepage of water coming from, let's say, rain. It's going to influence, it's going to help facilitate air entry, and therefore it's going to change your temperature. So we're looking for signatures. So now we want to look at simple signatures that tell us when a pavement is getting sick, when a pavement is getting is going towards poor performing. So it's then leveraging what I showed you before. We have about billions of data points of temperature data, leveraging that information to try to determine baselines of a healthy pavement, and then see how those signatures deviate. So we started first with processing using very simple descriptive statistics, using the mean, maximum mean, median, standard deviation, and look at how those distributions changes with time. So we did analysis for both concrete and asphalt. I'm going to give an example first with the asphalt. We have three sections, three asphalt pavement sections. Cell 2, cell 3 here showing same. So we have the same asphalt on top, and then we have full depth reclamation as foundation materials. But for cell 2 and 3, we have drainage. We have a good layer for drainage purposes, so water can flow. Cell 4 didn't have that. Cell 4 have the full depth reclamation right on top of the clay. So keep that in mind as you see those results, as I show you some results. So cell 4 didn't have drainage system. So then we start looking at simple data analysis of this big large data set from temperatures. So here I'm showing you, we have this thermocouple tree. So we have these three green sensors at the asphalt layer, and then these red ones in the foundation. Just showing you the sensors at the top, in the asphalt layer. So you can see here, interestingly, cell 4, you have this bimodal distribution, and you can guess why you have this bimodal distribution. But then cell 4 at the bottom, the sensor that is near the foundation has this weird behavior that kind of deviates from the expectation. So what we're trying to do is build these distributions, these signatures that we expect from healthy pavements that are recently constructed, and see with time how these expectations deviate as we have failures. Failures due to environmental conditions, failures due to traffic, or failures due to malfunction of the sensor. We have seen that too, which is pretty cool. Another one, cell 3. Cell 3, the top sensor is deviating from what we expected, weird distribution. And we came back and realized that actually that sensor was exposed at some point due to traffic. That there was very shallow, installed in the very shallow conditions, 0.5 inch, and eventually got exposed to the environment due to loading. Here showing you sections 2 and 3, not much distress, look pretty nice. Section 4 shows signs of distress. And when we were doing field investigation, we have DCP, we were running DCP, and we see the pore pressure, water pore pressure coming up, bubbles coming up here. And of course, we have a pond right next to it. And furthermore, we don't have a drainage system, so it was obvious that we're gonna have that issue. But it's very nice that we see it in the temperature data. The temperature is telling us, well, there is some issues really in the foundation in this cell. Close back the loop, and why the importance of intelligent compaction here. That we did intelligent compaction back in 2022 with David White again. Section 2, it shows everything is looking good, uniform and stiffer conditions. Here the colors are showing the resilient modulus of the foundation. Section 3 starting to show some issues, but not as bad. And section 4 is all red. Very poor foundation. So it's kind of intelligent compaction, and our temperature signatures are telling us, and visual inspection are telling us that there is something wrong with this pavement. So what we're looking here for is kind of proactively trying to address the issue before it becomes too bad. I'm gonna go very quickly. We have, how many more? Do we have like 10 minutes, right? Hopefully, let's see. It's until 2:30, right?
Yes, it's until 2:30, Dr. Velasquez.
Okay, I'm gonna go fast. I promised 35 minutes, but I got too excited. I'm gonna go as fast as possible. Now we have concrete. Concrete, very similar situation. We're looking for signatures. We have two pavements, cell 13 and cell 12 here, and cell 13. Both of them very similar concrete pavements, thickness very similar, a little bit different geometry, but this cell 12 have edge drains. Cell 13 didn't have edge drains. And then from the signatures, interesting enough, first of all, the mean as a statistical parameter was not given as much, because and we kind of extrapolated. Concrete is more stiff, is more robust, but standard deviation start giving us the information that we wanted. Deviation from in the standard deviation distribution was telling us that the pavement was getting some issues. And you can see here, we start to see bimodal distributions. So this is the cell 13, this kind of peaks like here. I'm going to zoom in more. I have another slide showing you that it's different from the 12, highlighting that problem. And what is very interesting too is that those two cells, by our current standards, roughness, IRI, were performing very good. 12 and 13, we didn't see any signs of issues with faulting or IRI. But after we did inspection, we did cuts and everything, cell 12 was looking good, but cell 13, dowels, you start seeing issues with erosion in the dowels and water pounding and issues with drainage. And again, IRI and other conditions of the payment, other assessments of the payment were not giving us that information that was something was about to happen. But this distribution of this analysis of signatures of our payment data was showing us. So this is the mean average distribution in your concrete in the payment slab. The mean was showing that both cells were pretty good, but the standard deviation was showing this bimodal distribution, and the cell 13 is the one with issues with drainage. So variation is telling, it was telling us you may have some internal issues, so be very careful, be proactive. So this is what we're looking for here, trying to be proactive and finding these signatures for asset management of payments. Now, as a closing remarks, I want to just to give you some lessons learned on implementation of geotech research. We got this information from a previous effort through the National Road Research Alliance. About a year ago, we have a conference, and we work extensively with Dr. Sharon Iden on doing these interviews with people across members of the alliance that collected us thoughts. And some of this information is super important, super useful for us to be successful at continuing implementation of geotech research. And this applies to any kind of research as well. So we collected information from agencies, DOTs, academia, and industry. And what are the thoughts that we got? And some of these are obvious, but it's important to keep emphasizing because we keep relearning, we keep understanding these issues, we'll hopefully start removing some of these barriers. So agency members, that is not just mean that we have about, I forgot, maybe 10 DOTs, part of the NRA. I will have to go double check, but we have now, we keep growing in terms of the alliance. So this is not just mean that. Some of the complaints about implementation, we do incomplete research. We need implementation support. This is a very valid one. We need to transition to implementation. We tend to do research, get all excited, finish it, put a report, and don't follow up. We really are vague in terms of guidelines for implementation. There is no really rigorous guidelines for implementation. We ignore payment foundation. I remember this is coming from a federal highway staff. He has a lot of issues that we don't pay too much attention to payment foundation. So this is not too general. Now, academia, the issues with research, with implementation is that sometimes they get too complex. We miss the holistic approach. We tend to silo in and to think too much about specific planning without thinking the big picture. We miss modeling the field. We tend to focus too much on the lab. Kind of the blaming game too. Industrial, there is barriers because of industry, because of regulatory barriers. Like it's kind of like typical. And then uncertainties, that's another barrier. And then for industry, we have sometimes they have hard time communicating with the research teams. They speak the same language, and I can see why. And then intersecting, we have this diagram because we want to see if there's intersecting thoughts. So there is some shared thoughts between the industry and academia. Technology transfer, not enough. So thanks to these events like that help tremendously. Cost, who shares the cost? Who shares the risk? Too much conservatism, very important. Research duration, it's too short. And again, risk is super important in the collaboration between those two teams. So you see these overlapping themes: communication, collaboration, who shares the risk. And the main one between the three of them that intersect was field application. We tend to not do a lot of field piloting testing, so maybe that's something to consider. More piloting testing, more field application of new technologies. Solutions, I'm gonna go very quickly, we have only 4 minutes. Go too fast. Okay. Solutions, we have spread the word, improve collaboration, mutual learning. That's from all the three hats. Agency and industry want to highlight that we need to do better researches at showcasing the benefits. Industry would like more open-minded, all stakeholders to be more open-minded, all the other stakeholders to take the risk. Industry tends to take most of the risk, so they would like to share it. Academia have other good points: field verification, be more holistic, be patient. That's a very good one. Include an implementation phase. Go back to fundamentals. I really like that one. And this one I cannot emphasize more. Champions is the most important, one of the most important things, and I'm probably biased towards the LWD success is because we have a very good champion throughout decades, and that's why LWD was implemented properly here. Champions is a key. Multidisciplinary approach include advanced modeling. Don't be afraid of some fancy computational tools that we have now available. Um, guidelines, design engineers, practitioners, specifications. And final thoughts, additional thoughts on implementation. Uh, those are personal. Those are not coming from these interviews from the NRA. We're missing proper credit in design stage. Practitioners tend to be biased towards an established standard solutions. We tend to feel comfortable and feel in our comfort zone, so it's very hard to get out of our comfort zone. We tend to focus on short-term fixes in our assets for transport for short-term fixes to solve our assets problems. And again, the recurrent one, siloing between functional groups is something that it will improve implementation of research like that, like the ones that I'm showing. I want to acknowledge Office of Materials and Raw Research mean that leadership and staff, especially research section staff, retired and former MinData employees. Some of them were involved in some of these projects that are not part of MinData anymore. Of course, Road Operations, the NRA, WSB was part of the geomorphology-based project, MSU, who is currently part of the geotech, vulnerable slope stability geotech-based approach, INGEOS and UTEP for the IC at Road. And with that, oof, I have only 1 minute for questions. That's good. I don't have a lot of time for questions. I did it on purpose. I'm just kidding.
Thank you, Raul. Thank you so much. It's a really a comprehensive presentation covering various aspects of geotechnical works at MINDAT. I have a couple of questions posted here. Maybe I will take those too. All right. The first one is, again, I was wondering if you could elaborate on the instrumentation used at Climax, Minnesota site. How was displacement of bridge piers and foundation measured? Was there a trend between the displacement and pore pressure measurements or precipitation data?
Yeah, good question. So we have shape arrays installed in several locations to track horizontal displacement of the slide. And really we wanted to find we have that shear failure. We have slickened sites conditions, and with those shape arrays, we really want to nail down what was the zone of the shearing zone. We do have pore piezometers installed to measure pore water pressure. We have some gauges installed down near the river to measure fluctuation of the river elevation. Bridge movement. We have just simple gauges, some gauges that are attached to certain locations of the bridge, and bridge staff goes often, maybe every month, to take photos of how that gauge is moving, is measuring deformation. So it's not very sophisticated. Now, however, we just started another project too, actually, with UNN and Auburn, on using satellite to start see if we can track movement of that bridge. So yeah, pretty much piezometers and shape arrays, and some gauges installing the bridge.
Thank you. The second question I have is for slope stability asset management, which is geotech based. What are the common failure mechanisms that you considered? Are there any long-term failures long time after construction is done?
Failure mechanisms we consider, which we pretty much right now we just have an inventory. We're working on trying to get to performance curves. So we have not defined yet what that performance curve look like. I will hope that we will go eventually to do some tracking of factor of safety as function of time when we change conditions. So in terms of failure mechanism, we'll pretty much focus on slope stability, kind of, for that specific asset, for slopes. Now, I want to emphasize right now, from my understanding from the Geotechnical Asset Management Group, man-made slopes are part of the inventory. So slopes that failed before, and then we put retaining wall or put geogrids or whatever reinforcement. But natural made slopes, I don't think they're still considered. They're still debated if we're going to include it or not. We're trying to follow the example. One of the main DOTs that leads the way in GAM is Colorado DOT, and they include both natural and man-made slopes. So we're thinking about including those two.
Thank you, Raul. I guess that's all I have questions. I mean, what I would do is at this point, I'll just ask Bora to do the closing. Bora?
Yep, thank you very much. First, Dr. Velasquez, then Dr. Perkins, Dr. Pupala, Elisa, and Hailey to make this webinar happen. Really appreciate it. And thank you all for attending. And again, Dr. Velasquez, thanks a lot for the webinar, but also thanks a lot for being researcher's voice in this field and championing the geomechanical related research ideas. So we really appreciate your support to our community and your service. And thanks a lot also for doing this webinar. We really appreciate all your efforts.
Thank you so much. And I didn't purposely include some of you guys' projects. It just came out. I thought it was this logical situation. It was not on purpose that I didn't include any Anand's or Bora's projects. So
Don't worry.
it was not intentional.
No, not
it's
at all.
all good.
Thank you.
It was
Thank you,
great.
Frank.
Thank you very
Appreciate
much.
it. Great job.
All right. Thank you.
Thank you.
Bye bye.
Bye, guys. Thank you, everyone.
Thank you all.